This video for MCET 450 Advanced Mechanics, we're going to review the basic types of stress that can be applied to an object or mechanical member. Image here, we have the first type, which is considered direct, normal, or axial stress. This is when you have a force normal to the cross-section of an object. This is the simplest form of stress. Notice we have a cylindrical object here of a given diameter, and the centroid of the cross-section is here, and we have a force applied of some value. It's being resisted with equal and opposite force on this end. And that's where we come up with the Greek letter sigma for stress, and sigma with the subscript A for sigma axial is simply force divided by area. And we can also extrapolate that to be force divided by pi d squared over 4, that of course being the area of a circle. Units are going to be either in terms of pascals for the SI system or PSI for the US customary system. The next type of stress we may encounter is bending stress. This happens when you have a machine member supported at one or both ends, subjected to a force applied somewhere along its axis. This force results in bending. To determine what the stress is in this situation, we need to look at a couple additional pieces of information. We need to know the length of the machine member, and we need to know the applied force, and we also need the diameter of the object. This is shown as a cantilever beam where it's supported on one end but not the other, and the force is applied at the unsupported end. In this situation, we have to find the maximum bending moment. For a cantilever beam in this situation, the maximum bending moment is the force times the length of the beam. Be careful, other types of beams will have a different type of maximum moment equation. This only applies to cantilever beams. Note here, cantilever only. And then we also need to know the area moment of inertia, which, because this is a circular cross-section, is pi d to the fourth divided by 64. Another thing we need to know is the distance from the centroid of the object to the outside edge. And again, because this is a circle, or rather circular cross-section, it's simply the diameter divided by 2, which is the same as the radius. Finally, after we have all this information, we can calculate sigma b, which stands for the bending stress, which is the maximum moment times the centroidal distance, which we know is d over 2, divided by the second area moment of inertia about the centroid. Next on the list, we have shear stress, and this form of shear stress is often called direct shear stress. And shear stress is typically annotated by the variable tau rather than sigma. And some books will use sigma for everything, and some will break them up between sigma and tau. I like it broken up this way because now you can distinguish more easily between an axial or direct stress or normal stress and a shear stress. There are two types of direct shear stress, and actually there's more than two, and we're going to get into that in later modules. There's multiple types of direct shear stress, but the two we're going to look at here are the average shear stress and the transverse shear stress. Something to be careful about on the transverse shear stress, it is subject to the shape of the object, the shape of the cross-section. For a circular cross-section, the transverse shear stress is 4 times the load divided by 3 times the area. Lastly, we have another type of shear stress, but it stands in its group by itself because it isn't the same as direct shear stress. This is called torsional shear stress. And in this case, again, we have a supported beam, in this case a cantilever beam, of a given diameter, and there's a torque that is applied about the centroidal axis. So this is one of those situations where it's trying to twist the object about its central or longitudinal axis. So this generates a torsional shear stress, and the formula for that is TC over J, where C is D over 2, just like in the previous equation that we looked at. It's the distance from the center or centroid to the outside edge, so it's effectively the radius in this case. The torque is the applied force times the distance at which it's applied. We'll look at an example of this momentarily, but make sure we distinguish that this is different than the bending stress. Right? It's not the force times the length of the beam. It means that this torsion is achieved by having a torque applied at some distance off of the centroidal axis. And you think about a wrench turning a bolt, right? That'd be like the body of the wrench would be that distance, or that S, for the displacement of the force that's being applied about the axis. And lastly, we need the polar moment of inertia, which is pi d to the 4th over 32. And with this information, we can solve this equation for torsional shear stress. So let's try this and practice it a bit. So here are a series of shapes that we can look at together, and we'll talk about what formula to use and then have you pause the video and attempt to solve them. So this situation, we have a force applied from the end. We probably can make this a little more specific and show that it's actually right on top, applied at the centroid. And then, of course, there's a support at the back side, equal and opposite. Application of Newton's third law of motion. And then we have a diameter given at 0.1 meters. So this is direct or normal stress, and this has an equation of sigma A equals F over A, which is A is the area, which would be the same as F over pi d squared over 4. There's the formula. Why don't you pause the video now and see if you can solve it, and then restart the video to see if you got the correct answer. I'll give you a moment to pause the video. Okay, hopefully you came up with an answer. Let's figure this out together. So we'll say sigma A is equal to F, which we said was 500 newtons, divided by pi times the diameter, which is 0.1 meters. Notice we're staying in the base units of newtons and meters. It will make it much easier to make sure you get the correct answer. So 0.1 meters, that gets squared, and then that in turn gets divided by 4. So what we'll find then is that sigma A equals 63,663. say 64 because it's 0.8, so we'll round that up to 64. Now what are our units? Well, we have newtons in the top here, right? And that is divided by meters squared. That's newtons per meter squared, which is the SI definition of a Pascal. So it's 63,664 pascals, and oftentimes once you get to the end, then we can convert it. That's equal to 63.7, we'll call it kilopascals. But don't convert until you get to the end. Do all your calculations in base units, and then you can convert at the end. Okay, next one to look at. See it? This is a case of what type of stress? Let's see. We've got a cylinder that is attached to a wall. It is free at this end. You have a force pushing down on the end such that it wants to try to bend it along the longitudinal axis. So it's trying to bend the axis, push it down. That's a definition of bending stress. And the formula for bending stress is sigma B equals MC over I. Now remember, this is a cantilever beam, so M, and we assume this is M max, equals force times L, and C equals the diameter divided by 2, and I equals pi d to the fourth over 64. Pause the video here and take a couple minutes to try to solve for the bending stress, then restart the video to see if you got the correct answer. I'll give you a moment to pause the video. Okay, hopefully you've come up with an answer for this one. So let's take a look at what we need to know here. So F times L will give us the maximum moment. We have 500 newtons times, this is 1.5 meters long. So that is 750, right? 1.5 times 500. And our units are Newton meters, which are the correct units for a bending moment. Our C value is D over 2, so that's 0.1 meters divided by 2 is equal to 0.05 meters. Our moment of inertia is pi times 0.1 to the fourth divided by 64, and that is equal to a very small number. It is 0.50 4908. Actually, we'll round it up to 0.9 because it goes pretty close to that. And you can obviously use scientific notation there to make that simpler to deal with. Okay, so now we should have everything we need. So we have 750 Newton meters times 0.05 meters divided by 0.000004909 meters to the fourth. Right, that's here. Let's see what we get for that. So we have 750 Newton meters times 0.05 meters divided by 0.000004909 meters to the fourth. Let's see what we get for that. So I'm getting 7 7,639,030. 7,639,030. Now if we think about this, we have Newton meters times meters. So that gives you Newton meters squared. You're dividing that by meters to the fourth. What you'll end up with is newtons per meter squared. Then that is, of course, pascals. And if we want to convert that, divide that by 10 raised to the sixth. And that comes up to 7.64 They're 7.64 megapascals. This is a situation where we don't necessarily know how this is supported, but we know that there's a force coming right through the middle, and we know that this is a given diameter. We have a force of 500 newtons. Again, notice I've kept these very similar so you can kind of see how they compare. And this looks like a case of shear stress, right? It's trying to cut through it. So in this case, what we'll look for is the average shear stretch, which is tau average equals F over A. So tau average is force divided by area, or F over A. So go ahead and pause the video, and we'll give you a moment to solve that, and then see if you got the same answer that I did. Okay, hopefully you've come up with a solution. And if you look at this, it's really the same equation as we had before. It's F over A. So we know it would be the same answer as we had up above. It would be 63.7 kilopascals. Now, even though you get the same answer, that's not the same type of stress. This is a shear stress as opposed to an axial stress. And a shear stress will have a different failure mode than an axial stress, and it'll have a different rate at which it fails, different strength that will be the limit for the design. So even though they have the same numerical value, they are two different stresses. Lastly, we have this one. This is an example of torsional shear stress. The diagram might be a little tough to understand what's going on. What we have is a cantilever beam attached to a wall here of a certain diameter. We used again 0.1 meters, but there's this paddle type mechanism attached to the center here, and there's a load on the paddle of 500 newtons, and the center to center distance of that paddle is 0.5 meters. So what this is doing is this is resulting in a torque, or a torsional load, that is trying to twist this tube, or this rod rather, about its centroidal axis. That's the definition of torsional shear. So what we'll start with, we'll figure out what the torque is. Remember, torque is the force times the distance at which it's applied. Force time, we'll use S so we don't confuse it with D for diameter. The C value, right, that we need for our equation is the diameter divided by 2. Next, we're going to need the polar moment of inertia, which is J equals pi d to the fourth over 32. And then finally, you'll be able to find the torsional shear stress, which is tau torsional equals Tc over J. And you want to keep in mind that this formula for torsional shear stress is specific to circular cross sections and would be different for other shapes of the cross section. So go ahead and pause the video and see if you can solve this one, and then restart it when you want to see the answer. Okay, so let's see how this solves. So the torque is the force times the distance at which it is applied. We have 500 newtons times 0.5 meters. So that comes out to be obviously 250 Newton meters. I'm just going to jot that up here. 50 Newton meters. This is half of the diameter. We found this before. This is 0.05 meters. The polar moment of inertia is going to be pi times the diameter, 0.1 to the fourth, divided by 32. Now, of course, we solved for the area moment of inertia of the same shape, and we found that really small number. So we can simply double that number. It's kind of a shortcut here. 9.82. That would be times 10 to the minus 6th, and meters to the 4. Kind of running out of space here. And finally, we can now find the torsional shear stress. So we have that torque of 250 Newton meters times the C value of 0.05 meters, all divided by that 9.82 e to the minus 6. So finally, I'm going to jump over here. Our T torsional equals 1272912. So 1,272,912, and that's going to be pascals. We can, of course, divide that by 10 to the 6th to give you 1.27 megapascals. That is our torsional shear stress. Remember, the polar moment of inertia is the overall resistance of the object to being able to be twisted. And so if you have a bigger number down here, it twists less, and therefore you have less stress. The smaller the number, the more it twists and the more stress you have, and the more likelihood you are going to have a failure. Okay, so that's it for this overview, and thank you for watching.